Okay, good afternoon and welcome to our first GReTA seminar after a reasonably good long summer break. I hope you all had a good summer. We have an interesting talk today. I wasn't quite sure from the abstract whether it's related, but I always had whether this relates to planar graphs and things like that, for example, but I always had the impression that one could do something categorical about these, but never got around to actually thinking about that. We'll see whether that is actually the case in a moment. The talk is by Malin Altenmüller, who is a PhD student in Strathclyde in Glasgow. And yes, I think she will tell us a little bit about where she is and what she's doing there before she starts the actual talk. So I won't take any more time with this. So please, Malin, go ahead.
Thank you very much, Heiko. And you may be correct that this is indeed to do with planar graphs. So there may be something you're interested in. So yeah, thank you everyone for having me. I'm quite excited to tell you about this project. Yes, and now here we go. So yeah, just half a slide about me. I am a PhD student in Strathclyde in the mathematically structured programming group, which is a group with lots of different people doing different topics. So we have a lot of applied category theorists, but we also have type theorists, and we also have logicians. And I'm kind of sitting in the middle a little bit, which I enjoy a lot. And I'm also currently a research intern at the programming languages team at Huawei in Edinburgh. And I'm working with graphs generally as a kind of intermediate compiler representation, which is also very nice. So kind of, it's all graphs for me, basically. So this is kind of what my PhD project is about a little bit. This is a very working title, which is theory and implementation of topology-aware string diagrams. So I'm interested in string diagrams. This is the kind of applied category theory side. They use string diagrams a lot. And about reasoning with these diagrams, and specifically with certain types of diagrams and how we can do reasoning on them. But I'm also doing the implementation of this. So I'm working with AGDA, the dependently typed programming language, and I'm trying to, or developing data types in this really rich type system, which express these graphs and diagrams with specific properties. But so this talk is more about the first bullet point, the kind of reasoning and the underlying categories of graphs for which we can do reasoning. So let's jump right in. So a recap maybe for you about string diagrams. So this is an example of a string diagram there, and they're used as a graphical syntax for terms in monoidal categories. So you'd usually have your objects being the wires, and then you have some generators, which is boxes, and then the whole diagram is a morphism in your category. And in a monoidal category, you can do composition two ways. So you can put things side by side, which you can draw quite easily by connecting the wires. But also you have, because it's monoidal, you have a tensor, so you can put things on top of each other or like in parallel as well. Which also is very nice in this kind of two-dimensional graphical syntax. So quite a lot of these coherence conditions, which you have to write out as equations in your monoidal theory, you can just draw and it's immediately the same in your graphical language. They're also nice to look at for human beings and to kind of think about what you're doing. And they're used to represent any kind of computational processes, so kind of some things with like processes which take inputs and they do something and then they produce some outputs. This is where there is these kind of input and output wires here. And then depending on what kind of or what specific property of your underlying monoidal category you have, you can observe these specific properties in your diagram as well. So the most classic example is a symmetric monoidal category where I can cross wires, I can change objects around, and then I have some coherences which say something like this. So if I swap and I swap back, then I get the same thing back. And so I am interested in a specific kind of string diagrams, which is exactly the kind that is not symmetric. So where this is not true. Why would I be interested in this? So the original motivation comes from string diagrams for quantum processes, because in a quantum circuit or in quantum processes, swaps aren't trivial. You can't just bake them into the theory. You have specific gates, which are swaps. So this, for example, you can do these 3 consecutive C0 gates, for example, and then you have implemented a swap, but you can't just, so this is an explicit operation, and it's not just an implicit, oh, I can just change wires around. And another example is, for example, printing circuits. If I print a circuit, I can't just cross over things because that would short circuit everything. And also having a theory that does not talk about or does not implicitly bake in swaps or like symmetries also means that it's more general. So I can specify or instantiate it to being then also symmetric by adding symmetry on top. But I can also instantiate it to be a braided monoidal category, for example, to have a braiding operation. So this is why we're interested in these kind of non-symmetric theories. Yes, full stop. So now graphs. So string diagrams are just a syntax at this point. They're kind of not really any real object or like mathematical object I can reason with, but I would like to reason with them. So I would like to do reasoning on my diagrams and not necessarily, and then by doing this, reason with my terms of my category. So I need some representation of my string diagrams where I can actually do this reasoning. And usually these reasoning for string diagrams works via a rewrite system. So you have a bunch of rewrite rules and you apply them one by one to your diagram. And this is how you can do all sorts of, for example, optimizations. So we're using graphs because they look very similar. Also, they have a really rich theory, like, yeah, like it's the obvious choice. And if you've seen this before, a remark here. So what I'm going to do is I'm going to translate my generator, so the boxes of my string diagrams, into vertices of the string of the graph. And I'm going to translate my wires of the string diagram into edges. In some other works, it's a kind of a bit of a duality where you use hypergraphs and so on. But in this case, I'm using, by optical kind of analogy, I'm using this translation. And then this reasoning of the diagrams by rewriting, I would like to do by graph rewriting. And I would like to do this in a suitable category and then do kind of categorical graph rewriting. So what I want is a category of graphs, kind of specific graphs, of these non-symmetric diagrams to kind of bring these two together. That's kind of the idea. So what kinds of graphs are we talking about? Well, so being kind of having this importance of this crossing edges means that we're not actually working with graphs, but we're working with graph embeddings or graph drawings. So a graph embedding is a drawing of a graph onto a surface. For example, here, this is two graph embeddings of the same graph. So you can see it's the same graph. It's got 4 vertices and 5 edges. And if vertices and especially the edges, if it's just sets, then these are the same thing. But the drawing is different because here I have a crossing in the middle and here I have not. So in this case, the right-hand side graph is a plane embedding and the left-hand side is not. So plane means I can draw it on the plane or equivalently on the sphere, because that's basically the plane with a point removed. And so I'm going to be mainly talking about planar graphs here, but in general, it's not restricted to planar graphs. I could as well think about embeddings into higher genus surfaces, like a torus, for example, so like adding holes for the oriented surfaces. So I could think about these ones as well, but the planar case is already enough to develop the structure, and then moving it into a higher genus case should not be too hard. So yeah, for now, I'm sticking with the plane case.
Sorry, can I just ask a quick question?
Yes, of course.
you said you said planar embedding is the same as embedding on a sphere, but isn't there a difference there?
So you have this translation that you have a sphere, and so once you have a sphere and you take a point on the sphere, you can do a projection down onto the plane. So something embedded being on the plane and on the sphere is equivalent.
Oh, I see. Okay.
So the lowest oriented surface is the sphere.
Okay.
Yeah, that's actually a pretty important point, that the sphere plays a role later as well. Okay. So thanks for asking. Okay, so other than graphs, we would like graph embeddings to be the objects. So how to represent graph embeddings? So then you look into your favorite combinatorial graph theory book, and you find the notion of a rotation system, which is for your graph, for each of the vertices, you don't store a set of edges, you store the order of edges around this vertex. So you can see here in this, on the left-hand side and on the right-hand side, especially this vertex, the order is different. And if you have an order for each vertex, this uniquely determines your graph embedding. So there's a bit of work here to do still, because you need to know, or you need to kind of figure out the surface and if it's oriented or not. But having a rotation for each vertex is enough to know your embedding. And this is the information we're going to use later. So now the plan is to define a category of graphs in such a way that it's easy to add rotation information on top of the vertices later on. So that's the whole plan, basically. Okay, and suitable category graphs also means that it has to be, I have to be able to do rewriting on these graphs. So let's have a look at how this works in category theory. So this is DPO rewriting, or double pushout rewriting. And we're just going to look at this in an example. So I've given a rewrite rule. So I have a left-hand side, which I want to rewrite to a right-hand side. And I kind of say, okay, so there's 3 edges that connect to these 2 graphs, and it's kind of the same. This is the thing I want to rewrite. So in my setting, I represent this as a span, where I have the common boundary, like these 3 edges in the middle, and then I have a map in whatever category you're in. So this is like a morphism in the category to the left and the right-hand side of the graphs. So this is how you represent your rewrite rule. And then the next step is to find the left-hand side within a bigger graph. So I need a match from the left-hand side into a bigger structure, which is this arrow here. So you can see this graph sits in the bottom left corner here, but there's also more vertices around. So this is the information I have available for double pushout rewriting. I have a rewrite rule and I have a match. And so there's now 2 things I'm going to compute. The first one is I'm going to remove the left-hand side from my overall graph, which is this thing. So I kind of go to the right here. And then I have a hole here and a context graph. And it's still connected with 3 edges. So I have this map as well. So that's the first step. And also, so this square on the left here is a pushout. And then the second step for computing the result is I'm now computing the pushout of the right-hand side to insert the right-hand graph into my overall graph. And that's my result. So this is the double pushout rewriting, which we'd like to be able to do with our category of graph. So here's a scheme of this again. So I have a rewrite rule from L to R, and they have a common boundary, which is B, just a graph. And then I have a pushout on the left-hand side, and I have this, and a pushout on the right-hand side. Yes, and crucially, all these maps are graph embeddings. So all of them are embedding something much smaller into something bigger. So to be able to do this, we need our category to have a few properties, which are that I have pushouts. Crucially, I can have pushout complements, and ideally they're unique. because I need to calculate this complement here, and it should be unique. And I need a notion of what is an embedding, because all of these maps should be embeddings. And very related, and basically this is exactly the definition of an adhesive category, which is designed such that double pushout rewriting does the right thing. So yeah, this is an adhesive category. Okay, and then I have on this diagram, I would like to make an observation. So if we just look at the left-hand side of this, I said that this graph down here in the middle is the graph with the left-hand side removed. So I'm kind of subtracting the left-hand side. So it's kind of the context with a hole. But there's a nice symmetry going on within this square. So if I now look at this as the context as just a graph, then on the other side, my left-hand side is basically the graph with the context removed. So there's a nice symmetry going on of, I have two disjoint elements and they make up together this graph G. And this will also come up later. So it's kind of, this is the left-hand side with a hole where the context will be. Okay, so this is a setup which we're working with and which we want to make work with our notion of graph category. Okay, so let's start from the standard graph category and then make some changes to our situation. So we start from the standard category where the objects are graphs. They are sets of edges and vertices, and I have two maps which assign a source and a target to edges. And then the morphisms between two of these things are a map between the edges, between the sets of edges, and a map between the sets of vertices, such that these things commute. So basically, the maps commute with source and target. So if I have the source of an edge, then it should still be the source of the edge in the target graph, and same with the target. Okay, so this is a standard category. So what do we do with this? Oh yes, and a remark. So there's going to be a lot of pictures in this presentation, and most of them are drawn undirected. I am referring though to this definition of graphs, but in the pictures, it doesn't really matter whether it's a source or a target. So it's just a bit unnecessary to see what's going on. Later on, I have like one situation where it's crucial, but otherwise it doesn't really matter. Okay, so now we actually want to define diagrams. And I said earlier, diagrams have some inputs and they produce some outputs, which means that we have some dangling edges in these diagrams, which are the inputs and the outputs. And also I said that, oh, we might want to remove some subgraph from a graph, which also leaves dangling edges around. So how do we do this? So there's different approaches. And there's like a lot of existing work on this as well. So you can just use open graphs, for example, where source and target are not always defined. Or you can use cospans, which is a similar thing, but the idea is always to somehow encode open graphs in your theory. But I'm interested in things that are sensitive to the surface they're embedded on, and dangling edges or like open loose edges don't play well at all with the surface, because any kind of graph morphism might just switch these dangling edges around, or so it's like very like it's basically no chance with open graphs to encode surface information, basically. And also I would like to add this rotation information, and if I don't have a vertex these edges are attached to, I can't add those either. So open graphs are not great for the case of surface embedded diagrams. Okay, but we're going to do something about this, which is this. So first of all, we take a graph which does have some open edges, and we draw a boundary around it and kind of identify everything as the outside of the graph, and we call it delta. And yeah, the input and output edges are attached to this boundary. Now I'm going to draw the same picture, but slightly differently. namely like this. And now it's important that things are embedded on a sphere, because you can imagine the rest of the sphere being kind of contracted into this region. So this is the same picture. So the outside is just a region of the graph. And then I use not a region, but I actually use a vertex to represent this outside region. So I have all my dangling edges attached to this vertex, which means that all my graphs are total, which is very nice. And also I can add rotation information to this outside. So I have kind of control of all these dangling edges. I pin them down into a single vertex and use it as the boundary vertex. And not only can I do this with the outside region of the graph, I can basically do this with any region of the graph which has loose edges. So whenever I have a hole in the graph, so this is taken from this earlier DPO diagram, I can do the same trick where I take a vertex and represent the hole with a vertex. So basically I could do this with each hole in the graph, or with, so there's very nice thoughts to be to be done, I think, of like maybe there's multiple outsides of a graph, or so specifically when we get to higher surfaces, this is a really nice thing to think about. Okay, so yes, so what if a graph has an outside and a hole? So for example, this boundary graph in the DPO diagram, which we'll see in a second, but I can do the same trick here. I just replace both of them with a vertex, but still have them connected. So this is exactly what we do. So a rewrite rule now looks like this. So in the middle, I have my boundary graph with a vertex representing the outside and a vertex representing the inside. But crucially, they're connected to each other. And then for the left and the right, I'd replace the inside vertex with a graph. And this is very related. So I copied this picture out of this paper down here, just to show the similarity. So this is double pushout rewriting of graphs with interfaces. That's what they're called. And here the interface in the middle is a discrete graph. And I map them onto edges in my graphs. And this is the boundary I can glue along my graphs together. This is very similar, except that in our case, the boundary graph is definitely not discrete. Like it should really be connected and have edges, because that's exactly where we store this rotation information, by saying how the outside and the inside are connected to each other. Okay, so this construction of adding vertices, kind of, like replacing regions with vertices is a thing we would like to do, because then we have control over the surface. So what does that mean for the category? So that puts some restrictions on what kind of morphisms we can have in our category, or we want to have. Yes.
Sort of conceptual question first. Yes. So I understand what you're doing. Sort of, but does that mean that the edges connecting to the red node here, they're actually deleted and then recreated?
No, they're not deleted.
So L actually preserves the edges, yeah?
L preserves the edges, indeed.
Okay, so
and there's going to be an interesting case a bit later where this will come up.
So you're going to explain to us that L is not a function on nodes, presumably, because the blue node maps to all of the four black nodes here. Yeah?
Yes, I'm really glad that this is exactly on the next slide.
Okay.
So this is exactly the conditions we need now for the morphisms, right? So if I replace nodes with something, my map on the nodes cannot be total. It cannot preserve all the nodes, but it has to be partial. So something like this, right? So I have my boundary vertex, and then I want to embed this graph into something bigger. So I need to replace this node with something else. So I definitely need to be partial on vertices, which is adding like some complexity. But yeah, this is what we have to deal with, or we will deal with. But then also, there's another thing. So we do want to be total on edges. We want to preserve all the edges, but we may not be injective on edges, because what if my context graph connects two edges together? So this should be a valid morphism in my category as well. So I map this edge onto, so I map both edges onto the same one, which means I'm not injective, which is fine in general, but then what's an embedding? Embeddings are exactly the injective things. So in this case, they can't really be, but this should also be a valid morphism. So these two things we have to deal with indeed. So yes. What? Yes, exactly. So what we're going to do is not see the vertex map and the edge map separate from each other, or at least kind of as separate, but to connect them a bit more together, which gives us the notion of flags around a vertex. So flags are the things, are the connection points of edges onto vertices. So each edge, so each vertex has, with all the incident edges, has a flag. So it's a pair of the vertex and the edge. And I'm also realizing there should be some, now there should be some direction information as well, but that's a technical detail. But it's these connection points. And then I have a flag map, which is this like action of this graph morphism on my pairs of things. And this is definitely partial because my vertex map may be partial, right? So I'm now going to characterize what I want my morphisms in the category to be, but also what I mean by an embedding on these flags. So for example, here, for this vertex V prime here, the vertex map is undefined, which also means that the flag map is undefined. So that's okay. But for this vertex down here, the flag map is defined for both of them. The edge map might not be injective, but we are injective on the flags. So both of these flags still exist after. So we're not identifying the flags, we're just identifying the edge. So bringing in these kind of two pieces of information for the edge and the flag and the vertex map together gives us the right notion of what we want.
Excuse me, there was a question on YouTube, which maybe is also relevant for understanding what comes on now. So the question was, can you explain how do you generate the right-hand side graph in page 14? So that's 2 slides back.
You don't generate it. You need to know this in advance. This is your rewrite rule, and you need to know what I'm rewriting for in the end. So this is not something you can generate. I hope. Okay, right. So, okay, this is flags, and we want to characterize everything by them. Okay, so this is an example, but okay, more crucially, so we have to do a bit more work. So let's look at this. So let's look at the property or this condition for morphisms in a standard graph category, where I have that my edge and my vertex map commute with the source and target maps. And we're now going by a counterexample, basically. So what if this happens? So this property is defined on edges, which means that if I have a vertex with no edges attached, that's a problem, because this arrow would be a valid one in this category, but I don't want it to be a valid one, because vertices represent the generators of my monodal theory, and they have a specific arity, and my arity of the generators should never change. So if this was a generator with like no inputs, no outputs, I shouldn't be able to just attach an edge. So, okay, we need to do something about this. So what if we take the condition and we kind of take the pre-image of it? So we now define it on vertices, and we take the pre-image of the source function, which gives me all the edges attached to this vertex. And then I map this across my morphism and check this. That's better because this case here would be covered by this because I start from a vertex. But then this other classic counterexample, what if I have a vertex where my vertex map is not defined. But then the top path of this diagram is not defined, but the bottom path would be defined. And that's not good because this should really be a valid morphism in my category. Okay, so other than taking the strict commutation of this, we're taking the lax commutation of this, which is exactly this case. So in this square commutes if either both paths are defined and are equal, or the top path is undefined and the bottom path is defined, then this thing also commutes. And that's exactly the situation we want. So we've ruled out this first one, but we have included the second one. And this is the condition we're going to use for the morphisms of a category. And we call this flag surjectivity because it kind of expresses that the number of edges around vertices are not increasing. Okay, so we demand this from all our morphisms. So now the definition of the category is my objects are total graphs, and the morphisms are pairs of edge and vertex map, where my edge map is total, and I have exactly this flag surjectivity property. There's other conditions which I'll talk about in a second. And then we define specifically what we mean by graph embedding by further requiring that the flag map is injective. And here I really mean the standard notion of injective, that two flags never get mapped to the same one. Okay, and this is a category, and this is going to be our category of graphs with circles. So a word about these other conditions and a word about circles. So I may have edges that have neither source nor target because they're actually loops, because this could well happen in my category of graphs. And this is also okay. Like, I'm happy to include these in my theory. But then again, flag surjectivity is now defined on vertices, and there's no flags here involved anyway. So we have to do something with it, but it's okay because we are using the edge sets of my graph as being an edge set and with source and target defined, and another set, which is the circles. And I can only ever go one way, so I can produce circles, then the edge becomes an element of O, but I can never go back from a circle into a normal edge. So this is a thing we can quite easily deal with, these loops. We just have to kind of bookkeep where the loops live. But maybe, and I'm going to talk about this a little bit later, this is something to think about. Maybe we need a little bit more structure than the loops being just sets, because we are interested in embeddings of graphs. So how about embeddings of loops? It's a very interesting thing. And I don't know the answer, so I'm going to explain to you the problem a bit later. Okay, so this is our category. And at the moment, it's all like we have this condition, but at the moment, the total graphs still have sets. It's all sets and nothing is ordered. So now we can add on top of this my rotation system. Oh no, okay, we're not doing this yet. We're doing this later. Apologies. Jumping ahead. So, okay, underlying graph category, because we actually want to do rewriting on them, right? So let's see. So unfortunately, this category is very specific with the partial maps and with this kind of very intricate condition. It's definitely not adhesive. So I definitely don't have all the pushouts, and I definitely don't have, but I know exactly in which situations I want to perform my rewrite, because I have exactly these spans with a boundary vertex and a dual and so on. So I know very specifically which situations I need the rewriting to work. And I'm going to show that my category has enough adhesive properties for these cases to do rewriting. And therefore, we define a few combinations of arrows in my category. The first one, and graphs. The first one is the boundary graph. We've seen this before. So I define this to be a boundary vertex and a dual boundary vertex, and they're connected by edges. This is my first definition. Then my second definition, which will show up in the DPO rewriting diagram, is called partitioning span, which is a span where the middle graph is a boundary graph, so exactly a graph with two vertices. And then I have two maps, one which is defined on the boundary vertex, but undefined on the dual of the boundary. So it's defined to substitute something for this delta bar. And the other map is exactly the other way around. So this one is C is undefined on delta on my boundary. So it's kind of embedding something into a context, but it is defined on delta bar. And these two characteristics of these two maps make up this partitioning span. And here is exactly the symmetry I told you about before, where one side I substitute one half of the graph, and the other side I substitute the other half of the graph. And it doesn't really matter which one's kind of the outside and the inside, because we're kind of on this sphere anyway. Okay, and then we can show, oh, there we go, that pushouts of these types of spans exist, and all the maps in the pushout are embeddings. So they are flag injective. So this is great because this is exactly what we need for rewriting. So this is for the pushout, and now for the pushout complement. So for like subtracting a subgraph, we define a similar thing, or like the kind of corresponding thing to partitioning span, which is called a boundary embedding, which here is a composite of arrows. But it's the same thing. So one of them is preserves the boundary vertex and does not preserve the dual. And the second map does not preserve the boundary. So this is a boundary embedding. And this is exactly the situation we want for the DPO diagram. And for this kind of embeddings, we can show that pushout complements exist. They give me partitioning spans, and they're also unique. And now comes the annoying part, up to degeneracies, which will be exactly the loops again, which I'll talk about. But yeah, so basically, crucially, we're only defining rewriting for the situations we actually need it. We don't need the whole category to be adhesive if it's adhesive in the case we need it to be. Okay. Now, this example again from the start. So this was the beginning, but we did have some dangling edges here, right? Or some loose edges here where we kind of want a context graph, but also here where we want something to be like have a hole where something should go in the end. So let's add some regions, which is the boundary, and also the dual boundary here, and then replace it with the representative vertices, and then it looks like this. So you can see all the graphs are total, and the rewrite works as expected. Okay, I really don't want to jump ahead again, but I think, oh no, okay. So now let's talk about loops. So look at this example. So now the directions are quite important, which one is source and target. Look at this example. This is a boundary embedding. And I know that my pushout is a circle. So I have kind of paired up the arrows here, and I need to pair them up differently on the other side to make a loop. And there's multiple solutions to this, which is why it's not unique, which is a bit annoying. And we call this kind of the re-pairing problem. We need to find another pairing to make a loop. And this thing has a plane solution. So where my context graph here is a plane graph. And then, yeah, I can draw this like a little bit wiggly, but it's a plane loop. But then also it has a solution where here the context graph is definitely not plane. And then I get something like this. And this is interesting, and I don't know enough about it. But this is a kind of non-planar drawing of a loop on a surface. I don't know if that's a thing or not. But like somehow this is definitely not a plane graph. So it's interesting to think about what's the characterization of a planar loop. Okay, so now it's the slide I was wanting to do all the time. So we've defined this category of graphs with circles. We can do DPO rewriting on it. And now we add rotation information, which is now very little additional work, because that's exactly why we defined the underlying category to be as it is. So we have as objects graphs, plus for each of the vertices, a cyclic ordering of the flags around them. And the arrows are the same as in the underlying category, plus an order preserving condition. And for example, if we look at the flag surjectivity condition, looks like this. So before we had the power set here of edges, and now it's a cyclic list of edges. So yeah, it's really not much change. And pushouts and pushout complements are the same as in the underlying category. Okay, so this is how we construct this category of rotation systems. And I have now two additional things, or two things I can do with this, or which I'm also going to mention. They're not as detailed as the stuff I've said so far, but I think they're still very interesting. So I'd like to share them with you. So the first one is, now we've defined this nice graph category and a rewriting system for them, we can get an instance of the operad of wiring diagrams, which is a construction by David Spivak in this paper. And it works the following. So on the left, we have an open graph, and I've kind of drawn little boxes to say that this is the outside region, basically. And the type of the whole thing is no inputs and two outputs, but there's no variables involved here. And then I have another. Okay, let me quickly go back one sentence and tell you what an operad is. So operads are like categories. So you have objects and you have maps between objects. But crucially, the maps take multiple arguments and give you one argument. So it's a generalization of a category. Okay, because now we have this diagram, which takes two inputs, two arguments, which is these two holes in the graph with specific types, and it produces an overall graph with these types. So it takes one input and two outputs on the outside, but it actually takes two. So in an operad, this one does not take any inputs, produces an output. This one takes two inputs and produces an output. And then composition for operads works element-wise. So if I have F composed with G at the first of its inputs, and for this operad of wiring diagrams, this means I substitute my G graph for the first hole within F, and then I get this result. And all of this works because we've just defined how rewriting works in our category. So I can actually do this with this category of rotation systems, which is a really nice instance of this. The holes being the arguments and the outside being the result type. It's a nice construction. Okay, and in the last 5 minutes or so, I do want to say a couple of things about the implementation, or give a rough overview or a few very interesting aspects of this. So I am trying to implement these kind of graph structures in a very rich type theory. And I kind of want to say, this is the type of planar graphs. And then if I do a substitution operation, I want to know that at the end, I also get a planar graph, like substitution preserves planarity and so on. And there's a few challenges here. The very first one being that graphs are cyclic structures, and we're in a functional programming language, which means we'd like inductive structures to reason about things. My graphs are finite though, like I can assume graphs to be finite, but they're still cyclic. So what I am going to do is I'm going to use a spanning tree of my graph. I choose a spanning tree, doesn't really matter which one at this point, and I define my graphs inductively along their spanning tree. So I'm storing basically a traversal. So here's a spanning tree. I'm storing a traversal And all the additional edges that are not in the spanning tree are also storing, but separately. So I kind of need to go from cyclic to non-cyclic things. Yeah, and there's a whole bunch of, so this is a very, very brief overview. There's a whole bunch of things about what do I need to do rewriting of a certain subgraph with something else and so on. But it's interesting. But the thing I wanted to say is that the structure of these additional edges, I said I'm going to store them alongside. The data structure I'm storing them alongside determines my embedding, because so spanning trees are always planar because they're trees, not graphs. And the additional edges determine which surface I can embed my graph in. And to show this, I can contract my spanning tree. I can contract any plane subgraph, and it will not change the surface a graph is embedded in. So I'm doing this, I'm kind of contracting everything together, and left over is all these additional edges. And in the plane case, I can use a stack to store these plane edges. So here you can see if I go around, I can always do a push onto a stack and then a pop when I arrive at the other end of an edge. So in the graph traversal, in the traversal of the spanning tree, it looks like this. I go along my spanning tree, and whenever I encounter this additional edge, I push it onto a stack. And then I keep traversing, and in the middle, I may do some more pushes and pops. But when I arrive at the other end of E, it's on top of the stack again, and I can pop it again. And this is exactly what a plane graph embedding looks like. So now the question, which is a really great one to think about, is what's about a higher genus graph embedding? What's the structure of these additional edges, or the structure of words, really, if I have a toroidal graph, or if I have something that's higher genus, which is a very interesting problem, I think. Okay, that was a very quick tour of this implementation, but yeah, these questions are, I think there may be answers in graph theory, and I'm only kind of touching the surface of graph theory, really. So maybe there's some experts that have some pointers for me. So overall, non-symmetric string diagrams are very interesting, not just for these quantum processes, but also in general, because they're the most general of the diagrams for crossings and braidings and so on. And if you want to control the embedding, or if you want to keep track of the topology, you can use these representative boundary vertices, which will give you this quite complex category, but I claim it's enough to restrict your rewrite rules to the cases you actually need for rewriting. And then in this case, we have these adhesive properties. And the fact that I have total graphs means I can extend them to the category of rotation systems. So some ideas, what about these loops? What is a toroidal loop? I don't know. What about more complex boundary graphs? So here we only had a boundary and a dual boundary being connected somehow. What if this was a more complex graph? What do we get? I also don't know. And then on the implementation, it's not a stack, but something more complicated to define higher genus graphs in the language. And with this, thank you very much for your attention and having me, and very much looking forward to questions and comments.
Okay, thank you, Malin, and yeah. So we have a couple of questions on YouTube. Let me just check. Maybe you can see them yourself if you switch the chat on. So right, one was a follow-up by MB from YouTube about that slide 14 and the right-hand side of that rule. Can you see that?
Ah, yes. My point was not to relate to its generation. It seems that the point delta bar has been removed. Right, okay. Yes, I'm gonna go to a slightly different picture. Maybe here. I hope this might be the right slide. So this delta bar is supposed to be removed in some cases, because delta bar is, so if you look at this graph down here, this is the context graph, and it has a hole here. So maybe, oh, this is maybe better. So it has a hole here where I want to kind of plug in either my left-hand side on the left-hand side or my right-hand side on the right-hand side. So this delta bar is representing a hole inside the graph, whereas delta is kind of representing the hole that is all around the graph. So it's basically the same idea with delta. But yeah, for kind of the inside. I hope this clarifies things.
Yeah. And you don't need the hole anymore in the right-hand side of that rule, and that's why
exactly. So for the rule up here, it's the same thing. So I kind of have the hole here, and on the left-hand side, I have the left-hand side of my rewrite rule instead of the hole, and on the right-hand side, I have the right-hand side of the instead of the hole.
Nick has a question, I think.
Thanks a lot, Malin. It was very interesting. I think also maybe following up on this. So I think on the next slide, you have the encoding with these blue and red dots, but really the arrows are not, as you said, not total functions, but each arrow is actually something like a span. No? I mean, you have certain kinds of span when viewed from the underlying host category of graph, which have additional properties, which you mentioned, these flag, surjectivity, injectivity, and so on, right? So, I mean, if I were to draw this as an actual diagram in graph, I would have I would have spans for every arrow, no?
No, so each of these arrows is a pair of a, so yes, you're right in that each of these arrows is a pair of a vertex map and an edge map, which satisfies these flag properties and so on. But
yeah, but actual... I mean, so basically the whole thing, if you absolutely must, you could, instead of having this partial map on vertices, you could actually parse everything out. I mean, this would be quite a large diagram. You would have basically, I don't know, 7 spans if I count correctly. But one could do that, right? And that would maybe clarify this whole matter about the vertices appearing or disappearing, because you said somewhere along the talk, these are partial on vertices,
yes,
total on edges, in the sense that these are spans.
Yeah. Oh no, it's not a span. This is just a commuting diagram condition. Let me find they are partial on vertices and total on edges, such that this holds.
Yeah, I'm saying, you said at the very beginning you're working with the category of directed graphs, and then you jumped to these kinds of flag maps. I think there would be a presentation where you would say, okay, I mean, this is not elegant, but I mean, one could, if an absolutely must, parse out all of the maps as spans in the actual host category, and then you have on top these rather non-trivial conditions for these flags, which then tell you something about the nature of it. And this, especially this partial order relation, could be parsed out if one must. I mean, I'm not saying this would improve the presentation. It's just that I think the confusion comes from that at some point you said you work in graph, and then you have diagrams which, of course, are not, total maps on vertices.
They're definitely not total, yes.
And I mean, at some point I was interested in this remark, because even without all the string diagrams, it's interesting to see. I mean, you say you can basically encode rewriting, let's say, where vertices retain their, how do you call this, the degree, or I mean,
arity,
arity, which is interesting in its own right. I mean, did you play with this a little bit? I mean, is it something you?
So this is coming from just the motivation that that these generators of string diagrams have. They're like given in advance, so they have a specific arity from the start, and that should be preserved along the way.
Okay.
Is that what you were saying?
And also, because Fabio, I don't think he manages to connect, but he posted on YouTube the question, you had a slide on the kind of conditions you put, under which then you have sort of this kind of adhesivity. I think the comment was that this is MN adhesivity. In a sense, exactly as you said, you identify a class of morphisms M for the, what you call, I guess, the embeddings.
Yeah.
And then you identify another class N which I think only were asked to be flag surjective, if I remember correctly.
Right, yes.
And then this combination gives you, I mean, that's a technique called MN adhesive, which Fabio works on quite a bit recently.
Okay, yeah.
Just
yeah, okay. Yeah.
Okay, so I pass over to Andrea, maybe. Thank you.
Yeah. I also had some question about the overall formalization and the relationship with standard categories of graphs we are used to use. So first of all, you started from string diagrams, okay, and you pass from the string diagram to a graph by taking as nodes what are in string diagrams the edges, basically the operators.
Yes.
Operators. Okay. You mentioned the fact that you basically have you can see them as bipartite graphs. Therefore, you can switch the role of nodes and edges. You can in string diagrams, for example, in the rule that you have shown. Basically, what are nodes? The wires are nodes, and the boxes are edges.
Yeah.
Okay. So my question is. Deciding what about planarity? So planarity of a graph is invariant with respect to the choice of what are nodes and what are edges in the specific choice you made at the beginning.
So I'm not considering the other choice of. So I'm definitely
at all. Okay.
Yeah. So I'm. This is just because there's some previous work and some quite well researched and work, and they do it the other way around. I definitely don't want to do it the other way around.
Okay, so you didn't.
No, I didn't think about this aspect.
Because planarity could be something that depending on the way you represent the graph, could be.
It would be different. Yeah, indeed.
Not in the. So it could be something interesting. And then my basic observation is that in this idea of having nodes representing boundaries. So if you want to, you have a graph, and then you want with another graph to identify a region of the regional graph, which represents, I don't know, the external part or the internal part of a boundary in general. We used to model this using standard morphism of graphs, but actually with arrows the other way around. So we take a node in the graph where you have the boundary nodes. The idea would be to identify a node which represents a certain region, to put a loop on it, and in this way, all the nodes in the ground graph, let's say, that will belong to this region are mapped via morphing to this node. So we have really a dual way to represent this idea of identifying in a graph certain regions, which could be the context of rewriting or typically the context of rewriting. And we use this representation in some definition of graph rewriting using a algebraic approach in the agree or double, what is the other name, push-out, pull-back approach, some recent approaches to graph rewriting. Do you have any comment about this? Did you consider having the morphism the other way around? Yeah,
so there is a lot of, I think this is a choice to make, but you could consider the kind of, this operation which is dualizing a graph. So for each face in the graph, you actually have a representative vertex, and then so there's different representations of the same graph, I think, and each of them will give you different instances of the same problem, I guess. So at this point we were mainly working on this representation, but I mean, it's definitely interesting to think about how to do it differently, if it would make it easier, I guess.
In our case, this is related to the way you have a sub-object classifier in the category of graphs. So how can you represent an injection of a subgraph into a graph by considering instead a morphism from the target graph to the subobject classifier, which is something where all the booleans in the category of graphs, and is related also to partial map classifiers. But it's okay. Maybe I can send you a link or.
That would be great. Yes.
About this, because I think there is some conceptual relationship in the way you represent boundaries graphs, even if technically the correspondences could be very.
Yeah. No, I'd be very interested. There's also a question in the chat about offline questions via email. I'm going to put this slide up because that's where my email address is, so please get in contact. But yeah, I'd be interested to see if you have a reference.
Okay.
Thank you.
Okay, so just to say, I'm going to have to leave now. So thank you very much for the excellent talk, and we can continue the discussion. I think Andrea agreed to continue chairing on my behalf. So I see you in a couple of weeks.
Thank you.
Thank you.
Bye-bye, Draco. Bye-bye. So I take over to Raiko, but I don't know if there are representations. Can we answer questions offline by email? Okay, yes, obviously, I think.
Right. So what I would suggest is maybe that we close the official discussion now and stop the YouTube stream. If anybody is on YouTube, you can find the link to the Zoom link if you want to join us. Still, we might stay for a bit to discuss, but we would stop the YouTube live stream now. And I would like to thank the speaker again. Thanks a lot, Malin. It was a very nice talk. And just to announce, we are back in 2 weeks with a talk by Jens Weber on also on a tool on I think it's called. Sorry, I forgot the name of the tool, but you can see it on the website. It will be back in 2 weeks. And I will stop the YouTube live stream now. Thanks for all the questions on YouTube. As I said, please do come over if you wish to still discuss